This lesson is the next step in linear equations where we're actually going to apply it now to linear inequalities. So just like we did on a number line where we graphed points, just dots when it was an equation, but when it was an inequality we shaded, we're going to apply that to two variables here with linear inequalities. So our objective is I can graph linear inequalities in two variables. So refer to your note sheet, and on this we've got two graphs that are on there. Just to give you an idea of what these are, we look at this and this is already completed. The equation for this line is what we don't see on this one. Just a reminder, if we were doing that, this would be, the line itself would be y equals, we have a y-intercept of 1, and notice our slope is we go down 2, and we go over a -1. -2 over -1 is the slope of 2. So it would be 2x and then plus 1 is the equation. Now because it's not an equation, but it's a dotted line, meaning it doesn't include the graph, we're going to change this from equals to a less than. Now how we know it's a less than is because if we look at this graph and we were to use this equation, any point that is on this side works. So if I put in 0, 0 into this, so 0, 0 is in the shaded portion. So if I put in 0, 0, is 0 less than 0 plus 1? It is. So that this side does have points that work. Over here, this point here, -1, so if I have the point -1 comma 0, if I put in 0 for y, -1 for x, is 0 less than -2 plus 1? Is 0 less than -1 is the final result of that? The answer is no. So this is not, doesn't make this a true statement, so we wouldn't shade on this side. So what we're going to do is we're going to graph the line, dotted if it doesn't have the or equal to, solid if it does, and then we're going to decide which side to shade it on based on which points in that region make it a true inequality. Let's check that out with this one. Over here, the inequality is given to us. Y is greater than the absolute value of x plus 1. This graph is the graph of y equals the absolute value of x translated up 1 unit to 1 on the y-axis. And then it's our typical v for this family of functions. And for this one, notice that if you have a dotted graph instead of a solid one because it's just greater than. And then if we test points, for instance, if we test the point 0, 0, the origin is a great one to use to test points. 0, 0, is 0 greater than 0 plus 1? And the answer is no. So it doesn't make it a true statement. So if you pick any point on this region down below the graph, it doesn't make it work. But if you pick a point up here, like this point here is the point 0, 2. If you put in 0 for x, and then you put in 2 for y, is 2 greater than 0 plus 1? That is a true statement. Any point you pick in this region up here will make it a true statement, so that's why we shade there. So in summary, what we're going to do is we're going to draw the function graph first, dotted if it's going to be without the or equal to, solid if it has the or equal to, and then we're going to decide, do we shade on which side of the graph based on do the points in that region make it a true statement or not. And all we have to usually do is test one point out of those regions. So let me give you some steps for this. So the steps for doing this, let me give you the steps in slope-intercept form for lines and also in standard form. So slope-intercept form, and then what if the equation were in standard form? So I'm going to give you both. You can actually convert standard form using our rules into slope-intercept form if you prefer. But for slope-intercept form, the first step is you want to go ahead and make sure you flip any inequalities. Flip this inequality symbol if it's a big if you multiply or divide by a negative. This is where we got to make sure you do that first when you get it into slope-intercept form, because if you don't, then you might apply the next steps incorrectly. So first of all, if it's a less than, or if it's a less than or equal to, then that means you're going to go below in this form. So anytime you get in slope-intercept form and you have it with these, you're going to shade below. And anytime you have a greater than or a greater than or equal to, you'll shade above the graph. Okay, so that's why it's critical to make sure you flip the inequality if you multiply or divide by negative to get it into slope-intercept form. Because if you don't, this step would be applied incorrectly. Here, if you have it in standard form, the key step is to go ahead and just test a point to see if it makes it true. Okay, so if you put that, that's kind of what I was showing you earlier. And so if it makes it true, so if you have a true statement, you shade on that side. And if it's a false statement, you shade on the other side. Or at least test to see if you shade on the other side. Okay, now the last thing I mentioned this verbally, but let's write this down. If you have a less than or a greater than, you're going to do a dotted line. And if you have a less than or equal to, greater than or equal to, you're going to do a solid line. Just like we did with open dots for this on the number line, and we had closed dots when we had the or equal to on the number line. Let's try these examples down here. So this one, y is less than 2/3 x minus 5. This graph, it's in slope-intercept form, so I don't have to worry about flipping the inequality because it's already in that form. I'm going to start at -5 on the y-axis, my y-intercept. I'm going to graph my slope, so go up 2 over 3. And now when I draw my line, I'm going to make this a dotted line because it's got a less than, not a less than or equal to. So I'm going to make this a dotted line when I graph it. And now I have to decide whether I shade above it or below it. Because it's a less than, I go below the line here. Now, just to test, just to make sure, let's test 0, 0, which should come up with a false statement because it's not on the shaded side. If we put in 0, is 0 less than 2/3 times 0 minus 5? And it's not. 0 is not less than -5. So this side is false. This side, if you test any point in this region, it will work. All right, let's try this one. This one is in standard form. You could put it, in a minute, I'll put it in slope-intercept form. But for this one, I'm going to graph using the intercepts. So I'm going to put in 0 for x. I get out, when I do that, -2y equals 4. So I get -2 for the y. Okay, when I put in x equals 0, I get y equals -2. And if I put in y equals 0, I put that into this, I get x is equal to 4. So that would be this point here. And now I'm going to shade that, because it has the or equal to, I'm going to make it a solid boundary line. So this is my boundary line between both regions. Now let's test a point. Now you may have noticed already that a great point to test in all these cases is 0, 0, because it's usually the easiest to test. So I'm going to, since 0, 0 is clearly in the region above it, let's test it out. Put in 0, you get 0 minus 0. Is that less than or equal to 4? That's a correct statement. So 0, 0 works when we test it. So we're going to shade above it. Okay, so that's my shade. Let's just try out, for instance, 5 comma 0 is in the area below it. If I put in 5 for x, 0 for y, is 5 less than or equal to 4? And it's not. Notice that's in the region we haven't shaded. Just to show you how this would look if you did it in slope-intercept form, I'm going to go ahead and put this into slope-intercept form. I'm going to subtract x from both sides. So I've got opposite of x plus 4. Now I'm going to multiply by negative 1/2 on each of them. Notice by multiplying by negative, that reverses my inequality. That's the statement up here. So I'm going to have negative 1 divided by negative 2 is going to be a positive 1/2 x. And then 4 divided by negative 2 gives me a negative 2. And so what I have is negative 2 is my y-intercept. I go up 1 over 2, up 1 over 2. And I've got my graph. And this tells me that I'm going to shade above a solid line. So it works out either way. It's now kind of a choice as to how you do it. All right, so we're almost there. This is our objective of graphing inequalities in two variables. This one has only one variable. You can think of it as 0y, but just a reminder, if we want to graph the boundary line, okay, the boundary here is x equals 4. Remember, that's a vertical line. So it's not a function, but it can be graphed as a linear equation. And so x equals 4 is going to be straight up here at x equals 4. I'm going to do a dotted line because it's not or equal to. So vertical line there at x equals 4. Now I've got to decide whether I shade to the right or to the left. Well, it kind of makes sense in this format that all the x's less than 4 are to the left. And so I'm going to shade over on this side of my boundary line. If you want to test a point, again, 0, 0 is clearly to the left. If you put in 0 for x, is that less than 4? It's a true statement, so yes. And if I tested 5 here, is 5 less than 4? It's not, so it doesn't work. So in summary, when we're doing the inequalities in two variables, when you're doing linear inequalities, what you want to do is have either slope-intercept form or standard form. You remember that you're going to shade this graph rather than just the boundary line. The boundary line will be a dotted line if you don't have the or equal to, a solid line if you do, and then you do a test. If it's in slope-intercept form, this tells you whether to shade below, this tells you whether to shade above. You just have to know above and below the graph. But otherwise, you can always test a point. If you put the ordered pair into the inequality and test it, if it works, you shade on that side. If it doesn't work, it's not true on that side.